Fermat's little theorem tells me that when I have prime as my modulus, then any number not congruent to 0 mod that prime raised to the p minus 1 power is congruent to 1. And this is based off the idea of being a unit.
Is this for section 24?
Yep. Now, normally FLT reads Fermat's last theorem, which is much more complicated than this, but we're only using it in the context of Fermat's little theorem here. But as a consequence of this, we end up with some really interesting number theory applications. And trying to do number theory applications leads to some questions about divisibility. It leads to questions about what we know about numbers. So here's a really interesting claim. I don't care what number you pick. Raise it to the 33rd power, subtract the original number. The answer is divisible by 15. You gotta be kidding me. How the hell do you know that? First of all, I want to know the wise ass who came up with this result. But, interestingly enough, patterns in numbers and divisibility in particular go back almost 4,000 years. Before Greek mathematicians, both Babylonian and Egyptian mathematicians examined properties of numbers related to how they divided into each other, how we drew figurate numbers, we got powers out of that idea, and they assigned characteristics to numbers. Masculine, feminine, good numbers. This is where we get the description of numbers that are perfect, equal to the sum of their divisors, and abundant, being more than the sum of their divisors, or deficient, less than the sum of their divisors. But all of these come out of categorizations of the behavior of numbers attributed to Greek and pre-Greek mathematics. So they did a lot of weird studying about what divides what. And this is one of them. How can I use Fermat's little theorem to demonstrate this? I'd like to prove this. When all you've got is a hammer, everything looks like a nail. Fermat's little theorem is the hammer. How do I apply it?
Isn't it just the AP minus 1, so you change it to N 32 and go from there?
There's just one problem. I have to be dividing by a prime. 33 isn't prime. 33 is 3 times 11. And neither is 15. I don't think that's a bad idea, but I need to figure out how to apply it in this case. And I can't do it with 15. I can't do it with 33.
You do with like 31.
Yeah, but I'm trying to divide by 15, right? If I'm trying to divide by 15, that's the part that should be related to the power. So that's my problem. That number's not prime.
If you can show that it's going to be divided by 3 and 15, not 3 and 15, 3 and 5, is that the same thing?
And 3 and 5 are both prime, right? If you're divisible by 3 and you're divisible by 5, you have to be divisible by 15. Okay, so let's attack it that way. We're going to use two different primes, Noah. Instead of using 13 or 15 at all, we'll try and do this for 3 and 5. So let's see if we can use this to show divisibility this way. You want to do 3 first or 5 first? Okay? No matter what number I pick, Fermat's little theorem says, oh, n squared is going to be congruent to 1 mod 3, unless n is a multiple of 3, right? What's the corollary to Fermat's little theorem? Very last thing we did for the examples Tuesday.
A to the p is congruent to a to the p.
So I can also look at n cubed instead of n squared, right? All right, we'll get back to that. As long as 3 doesn't divide my number, n squared is congruent to 1 mod 3. Now, let's think about n to the 33rd. Actually, wait a minute. 33 in terms of 2, right? So n to the 33rd is n to the 2 to the 16th times n to the 1st. So let's now go mod 3. That would be congruent to 1 to the 16th times n mod 3. Wait a minute, 1 raised to any power is just 1. So n to the 33rd is congruent to n mod 3. What does that tell me about n to the 33rd minus n? Mod 3, congruent to 0. Which means 3 goes evenly into it. 3 divides into n to the 33rd minus n. Hey, it worked. Repeat this process with 5. And you verify that 5 divides evenly. Now, I do have a caveat here. We said here that this works when 3 doesn't divide n, right? But if 3 does divide n, then 3 has to divide this expression, n to the 33rd minus n, because it divides each piece. So that covers when it does and when it doesn't. could make a note to that off to the side. So I have to do the modular argument when it doesn't. I don't have to do the modular argument when it does, do I? So that covers all the bases. What do I change when I do p equals 5? No?
Like the addition part,
Here,
when you do it by 5, yeah. No.
I don't do it by 5. I do it by 4s. If my prime is 5, then n to the 4th is congruent to 1 mod 5. And then I write 33 that way, in terms of the 4th power. Quotient remainder, please. There's the critical piece again, isn't there? N to the 33rd is n to the 4th to the 8th times n to the 1st. If I go mod 5, that's 1 to the 8th times n, which means that n to the 33rd is congruent to n mod 5. And again, I need that same little extra bit. If 5 does divide n, then 5 also divides n to any power, which means that 5 will divide the difference of those two powers. Again, at the moment, this seems like kind of just mathematical playing around. I promise there's a reason to understand this level of divisibility coming. Questions? All of this assumes we are working in a prime. What if not? How can I rephrase or rearrange or re-examine the argument that Fermat gave me? All right. The reason we were able to make a to the p minus 1 congruent to 1 in the proof of Fermat's little theorem was what? Back and look at Tuesday. one critical reason. Oh,
Is it like when we were like making the tables and when it was prime? Wait, no.
there's something about the table when it was prime, but it was the table for multiplication.
It was like, I don't know, there's like a 1, 2, 2, 1, and then the other graph was like a 0, 2, 2, 1. It was like,
So what did we say about that table? Just a couple of sentences later.
it's a field.
Yeah, that's a great claim. I said, you all bought it, nobody questioned me. I said, not only was it a field,
It's multiplicative non-zero elements.
they were all units. Had inverses. All right. So let's figure if I'm in a group and Zn and n is not prime, then what do I know? I know that not everything is a unit. So let's only look at the ones that are units. I apologize, we've used U for the unit circle, now I'm using U for units. The name of the group depends on what universe I'm operating in, but I claim that's a group. Under multiplication mod n. Now I'm pretty sure we did that as an exercise. But let's walk through it again. What do I need to be a group? Closure. So if I have two units and I multiply them together, I get another unit. How would I show that? Pick two units. Being a unit means multiplicative inverses. So there exists A inverse and B inverse. And since those items have multiplicative inverses, they're in U. Hey, wait a minute. Along the way, we've picked up problem number 3, property number 3. It's got to have inverses in it, right? Well, the definition of being a unit means you have a multiplicative inverse. That property is automatically satisfied. Let me make a note down here. I got to remember that. We get units have inverses by default. That was property 4. I want to show that AB has an inverse, right? Is there something I can multiply by to get AB times that thing equals 1? But AB to the negative 1 is the thing I'm trying to find. I don't know that AB has an inverse yet.
Multiply by B inverse times A inverse.
Because I get associativity from Zn. That takes care of property 2, by the way, which was, is this thing associative? Because then AB times B inverse A inverse, rearrange the parentheses. So it's a 1 in the middle, which gives me A times 1 times A inverse, which gives me A times A inverse, which is 1, check mark. Wait a minute. Does 1 have a multiplicative inverse? Which means I have the identity. That's property 3, property 1, property 2, property 3, property 4. This is a group. The set of units is a group. I don't want to call this group U. I want to call it a group. I'll call it G, damn it. So we'll call it Gn. Now here's the interesting part. If n is prime, that's all the non-zero elements. But if n is not prime, this is some subset of the non-zero elements. It's a subset, but scratch that. That should be n. The n is a subset, but not equal to Zn star. Somebody give me a non-prime number. Okay? What are the units in Z4? There aren't very many numbers. You can calculate this directly. What has to be a unit? Unity. That really only leaves me two other choices, right? Because you can't do 0. 0 doesn't have an inverse under multiplication, so it's either 2 or 3.
No.
Why? If 3 has to have a multiplicative inverse, what is its multiplicative inverse? What times 3 equals 1 mod 4? 3 times itself. 2 times 1 is 2, times 2 is 0, times 3 is 2. So no matter what I multiply by, I never get 1. We had a way of figuring out whether or not a number was a unit.
Isn't it like whatever, like take an element in that set, if the greatest common divisor between n and that element is 1, then it's a unit?
And the other ones, whose greatest common divisor is not 1, those are 0 divisors. So I want to count the number of things less than n whose greatest common divisor is 1. I'm going to define a function. That's a lowercase phi. Phi of n is the size of the set numbers less than or equal to n that are relatively prime to n. This is called the Euler-Tauschit function. Almost nobody remembers to call it that, the Euler-Phi function. And what Euler noticed is that if we restrict ourselves to the universe of units, then Fermat's theorem should still work. In Z4, units were 1 and 3. Yes.
Is that a less than or equal or equal to a to n?
Yes. Because the greatest common divisor of n and n is not 1, it's n. So that one doesn't contribute no matter what. One squared is 1. 3 squared is 1. Those were the units. Yes? Another composite number. Well, 5 doesn't work. Let's go to 6. What are the units in Z6? What's 1 squared?
1.
5 squared
And mod 6 is 1.
is also 1. What are the units in Z8? Oh, wait, there's more. Anything that's odd, right? Because the only divisors of 8 are even numbers. So 1, 3, 5, and 7 are all odd. I need your calculators. 1 to the 4th is 1. 3 to the 4th is 81. But I'm modding by 8. Aha! 5 to the 4th. Why I told you to get your calculators. 5, 25, 125, 625. What's 625 mod 8? I would be a good assumption. Tell me if I'm right or wrong.
624.
624 is a multiple of 8. 7 to the 4th. 7, 49, 343, 2,401. 2,400 is divisible by 8. I wrote them down.
That was crazy.
I will tell you that I've been doing powers of 5 and 7 for a very long time. I have some of them memorized. I don't go much past that. The advantage, 7 squared is 49, that's almost 50. So 7 cubed is 350 times 7, take away 7. 343. Wait a minute, 300 times 7 is 2,100. The other part, 43 times 7, that's 301. 2,401. I can't do any of the rest of them. Was any of you see the movie Ender's Game? It's not a recent movie, unfortunately. Pretty good sci-fi book. Decent story. In the book, Ender is a very picked on child, and he decides to control his emotions by reciting powers of 2 in his head to see how far he can get, keep himself under control. So yeah, I learned a bunch of powers of 2. But I learned it because back in my day, I bought a Commodore 64, and the very first thing it did when it pulled up is it checked all the memory. And so it said 65536, ready to go. That's 2 to the 16th. It checked all of the memory spots available in a 16-bit computer. I learned the powers of 2 up to 2 to the 16th. So we have powers, but wait a minute. The fact that there were 4 units is the reason I could do this. The fact that there were 2 units is the reason I could do this. Euler says if the greatest common divisor of a and n is 1, then a to the phi of n is congruent to 1 mod n. In primes, phi of n is n minus 1. Euler was able to generalize Fermat's little theorem to work in rings that were not fields. By restricting ourselves to the collection of units within that ring, I am still able to take larger powers. So let me try and do the same sort of problem that we were doing with Fermat's little theorem. I would like to know what 5 to the 6th mod 9 is. Now, this is a number small enough we could do it on our calculator. Let's see, we just did 5 to the 4th was 625. Multiply by 5 again, I get 3,000 plus 125, 3125. Multiply by 5 again, that's 15,000, 125 times 5 is 625. 15, so I can do 15,625 divided by 9. I don't want to do it. Division's harder than powers, so I don't want to do it that way. What I need to do instead is I need to know what's phi of 9. So what I need you to tell me is which number is less than or equal to 9 of greatest common divisor with 9 equal to 1. I find the easiest way to do this write down all the numbers less than or equal to 9 and cross out the ones whose greatest common divisor isn't 1. Greatest common divisor with 9 isn't 1. I'll say the sentence properly. What are the things that divide 9? So 3 is going to have a greatest common divisor of 3. 6 is going to have a greatest common divisor of 3. 9 is going to have a greatest common divisor of 9. Greatest common divisor with 1 is 1. 2 is prime. 4, no 3s in any of the remaining numbers. And for the record, 5 to the 6th is 15,625 is 9 times 1736 with 1 left over. There's another way to do this that we did back in discrete, called modular exponentials. And when I did it, y'all thought I was out of my mind. What's 5 squared? Mod 9? Here's some type. 5 times 5?
25.
Mod 9.
So
So 5 to the 4th would be congruent to 7 squared mod 9. What's 7 squared? See,
49.
mod 9. Because 45 is divisible by 9. So if I want to do 5 to the 6th, I can do 5 squared times 5 to the 4th. And in the universe of mod 9, that's 7 times 4, which is 28. What's 28 mod 9? We did the binary expansion of the power. That's 1, 2, and 1, 4, and then I just have to write the correct multiple. I know I did this. One of the last algorithms of chapter 4 in the discrete book. Again, 5 to the 6th is not a very big number. 5 to the 283rd, well, that's a much bigger number, isn't it? I'm probably going to want to do this exact sort of thing on a computer if I'm dealing with large numbers. But these algorithms need to be done in that fashion to be able to do these large powers. Questions? I want to try and solve equations. That's what algebra is about, damn it, solving equations. So I want to solve equations in ZM. Or equivalently, I want to solve those equations mod M in the integers. I know there are cases where that has a unique solution. When will this expression have a unique solution? Not always going to work. Might.
A and B are relatively prime.
I don't need A and B to be relatively prime. Why would I need A and B to be relatively prime? Where are you going with that?
Although there was a homework problem where it was like 3x's compared to 2, and they have one solution per.
But what field?
I think it was Z7 and Z23.
And in that case, it's not that 3 and 2 are relatively prime.
Isn't that they're relatively prime to the field of general?
They're relatively, 3 is relatively prime to the field. Why? Why would it matter that A and M are relatively prime?
As a unit.
And if A is a unit, it has a unique inverse. And we have a unique solution. And what you've just written down, Reese, what you just told me is the proof of that theorem. If I'm multiplying with a unit, then I will have a unique solution. Now, the other way to think of this, instead of thinking just in Zn, is to think, Zm, is to think in the integers mod m. Let's just think in integers. If m is a natural number, a an integer with greatest common divisor of a and m equal to 1, then ax equals, congruent to b mod m doesn't have a unique solution, but it has one residue class, one congruence class as a solution. So we'll get a whole set of solutions, but they'll all be congruent to the same thing, mod m. What? Three x equals 2, right? In Z23, Z7, whichever, which one you want to look at. Okay. So I'm going to take that problem and rewrite it like that. Three has a multiplicative inverse in Z7. I can't divide in integers, so I have to multiply by the appropriate inverse. What's the inverse of 3 in Z7? What times 3 gives me a remainder of 1 when divided by 7? It's not 3 times 1, 3 times 2. Those are both smaller than 7. 3 times 3, remainder of 2. 3 times 4 has a remainder of 5. 3 times 5 is 15, remainder is 1. So to solve this equation, I multiply both sides by 5. On the right side, I get a whole set of numbers, but on the left side, what's 5 times 3 times x? Oh wait, mod 7, that's just x. So what you're telling me is that the whole set of numbers that do this is any number congruent to 10 mod 7. What's the smallest positive number that works for? Positive number for which this is true. 3. So if I were in Z7, I would say the only solution to this problem in Z7 is 3. We have a unique solution. But in the integers, I end up with a set of numbers. Pick any of those numbers, plug them in, multiply by 3, the remainder when you divide by 7, it should be 2. And this is one of those congruence classes, mod 7. All the numbers whose remainder is 3. Questions? All right. What if they're not relatively prime? What if A and M are not relatively prime? Well, no. I should be able to fix this somehow. Again, Euler comes to the rescue. And he says what you really need to look at is what happens with your common factor, because you'll have a greatest common divisor. If it's not 1, then it's got to be something else. Let's call it D for divisor. I'm still trying to solve this equation, and I claim this only has a solution in ZM if, and only if, D divides B. As a matter of fact, the problem is that we don't know A is not a unit, right? If the greatest common divisor of A and M is not 1, then A is not a unit. So I can't multiply by the inverse. I'm not going to have a unique solution. As a matter of fact, I'm going to have D solutions. I beg your pardon? This one's safe. Here's an example. We are working in the universe mod 9. There are only 9 numbers, 0 to 8. I would like you to run an experiment for me. I would like you to multiply by 3. 3 times 0, 3 times 1, 3 times 2, all the way up to 3 times 8. Give me the remainder is mod 9.
That includes 9, right?
No.
No.
0 through 8.
Oh, okay.
X is 0 through 8. please notice, you get a very restrictive set of answers, don't you? You only get
036.
0, 3, 6. You never get 8. What's the greatest common divisor of 3 and 9? Not 1, it's 3. Does 3 divide 8? Nope. This has no solutions. This has a solution only if the greatest common divisor divides the other number. GCD of 3 and 9 is 3. 3 does not divide 8. No solutions. But since there were very few numbers we'd actually look at, I figured we'd do it the hard way. Now, what's interesting to me is that a lot of the problems written in the text actually are written poorly. The problem that I stole this from actually was this problem. And the first thing I did when I saw that problem is I said, why the f are you asking me that problem? 39 and 125 are bigger than 9. But remember, I said we could do these problems in the integers as well. And that's what's different about the way I've written that theorem, is I've written that theorem for Zm. But it also applies for all integers. Same exact idea. If AX is congruent to B mod M, I only get a solution if the greatest common divisor of A and M, which I will call D, divides into B. And in this case, the greatest common divisor of 9 and 39 is 3, and 125 is not divisible by 3. But if you actually do divide by 9, the remainder of 39 divided by 9 is 3. The remainder of 125 divided by 9 is 8. So this problem is congruent to this one. I don't want to work with numbers that are larger than my modulus if I don't have to. So I'm going to try and do that first. But it's not required. Questions? This is an example where we had no solutions. If I have solutions, I get more than one. Fumble. Now, does this have a solution? Why?
greatest common divisor of 18 and 15 is 3. And you can divide 27 by 3.
So I'm going to do two things. I'm going to reduce all the numbers to be smaller than the mod. And then I'm going to divide by the greatest common divisor everywhere. So the only number that is bigger than 18 is the 27, so I reduce that first. And now I say, I don't want to work in Z18. I want to divide by the greatest common divisor. Across the board, I'm going to work in Z6. Now, why does this make me happy? Because I'm a sick mother. No, I promise. There's a real reason this makes me happy.
Because 5 and 6 are relatively prime.
And that means 5 is a unit in Z6. 5 has an inverse. But notice I'm working in Z6 now, not Z18. I'm going to have to do something about that later. What's 5 inverse in Z6? We wrote that down earlier. 5 times 5 is 25, congruent to 1. 5 inverse is 5. Which means, how do I solve this?
Both sides by 5, and then reduce whatever. Yeah. It would be like congruent to 316.
So I reduce that and I get 3. Which technically means I have an infinite collection, the congruence class. 3. And all of the numbers congruent to 3 mod 6, right? How many of those numbers appear in Z18? I need to go back to Z18. The answer to this question is the greatest common divisor of A and N. Greatest common divisor that we divided by up here. There are 3 of them. What are they? 3 of them. You only gave me 2 numbers.
Sorry.
3, 9, and 15, right? Guess what? We don't have one solution. We have 3. Ta-da. Now, again, you should check. 3 times 15. Mod 18. Okay, wait, 18, 36, 45 minus 36 is 9. Use 9, 15 times 9. I told you to get your calculators out. I promised it wasn't going to be used a few times. 135. 135 divided by 18. What's the remainder? 135. 135, so 90, 36, 126, 135, take away 126 is 9. 15 squared is 225. 225 divided by 18. What's the remainder? Yay! Now, in the integers, I actually get 3 congruence classes. For solutions, instead of just 3 numbers. Solving linear congruences, finding those remainders, is a key piece to what we are going to do next. The basis of modern encryption, solving these equations. So I'd love to tell you this is useless crap. This is what's keeping your credit card numbers safe on the internet. This is what's locking your bank account numbers. This is what the hackers have to undo. Intercept your messages. How? Why? Because I'm not going to use small numbers. I'm going to use huge numbers. And I'm going to use huge numbers because they are hard to find. Large prime numbers. Very difficult. But I'm not just going to use one large prime number. I'm going to use 2 of them. I'm going to multiply them together. So you have to factor this giant large product of numbers. It's easy to factor when you know the small factors, but if I multiply by 2 giant prime numbers, none of the factors are small. We're in deep try and crack that, aren't we? Tuesday. Tuesday is about encryption. This largest prime number was found less than a month ago.